Welcome to our demo of ERP Next, which is a comprehensive enterprise resource planning solution. It is designed to streamline and simplify your daily business operations. Here we present TinPack Industries, a complete demo ERP solution to simulate the end-to-end processes of a paint container manufacturing company. For our demo purposes, we assume TinPack produces 15,000 round tin containers per day for customers like Asian Paints and Nerolac Paints. Today we'll walk through the entire business cycle, from receiving a customer order, to purchasing raw materials with quality gates, manufacturing on 3 parallel production lines with operator-level tracking, quality inspections at every stage, and finally delivering finished goods to the customer. Before we look at the ERP transactions, let me walk you through the engineering behind a 4-liter paint container. This document shows how we break down the material calculations, from raw tinplate sheets all the way to finished containers. I will be sharing this document with you for your reference. The product is a round tin container, 165 mm outer diameter, 187 mm fill height, which holds exactly 4 liters, and 210 mm total body height including the seam allowance. The body blank that gets rolled into a cylinder is 518 mm by 210 mm. 518 being pi times the 165 mm diameter. The finished container has 3 components: a body, a bottom which is seamed permanently to the body, and a lid which is packed separately. End customers are Asian Paints and Nerolac Paints. Daily production target is 15,000 containers across 2 shifts of 7,500 each. 3 production lines feed into this. The body line uses 0.28 mm thick sheet, 880 by 1040 mm, and runs through 5 operations: slit, epoxy coat, prime, print, and punch. The bottom line uses a thinner 0.20 mm sheet, 900 by 600 mm, slit and circular punch. The lid line uses 0.28 mm sheet, 900 by 600 mm, slit and circular punch. Let's look at the cutting mathematics for each line. This is where it all starts: a tinplate sheet, 880 mm wide, 1040 mm long, 0.28 mm thick, weighing 2.01 kilograms, costing 235 rupees per sheet. The first operation is slitting at the shear M1. We cut this sheet into strips. How wide does each strip need to be? The body height is 210 mm, but we need 5 mm extra at the bottom for the seam hook and 5 mm at the top for the flange. That gives us 220 mm total strip width. Now, 880 divided by 220 equals exactly 4. 4 strips per sheet, 0 edge waste. You can see it in the diagram: 4 strips, perfectly tiled, no red scrap areas. The scrap at this operation is just 0.001 kilograms, essentially 0. The sheet dimension was chosen specifically for this container size. When your sheet size divides perfectly by your strip width, you eliminate slitting waste entirely. Per shift of 7,500 blanks, we need 3,750 strips, which means 938 sheets. Sheet cost per shift, 938 times 235 rupees, is rupees 2,20,430. The output item is a body strip for the 4L tin, ready for the next operation. After slitting, the strip goes through 3 coating and printing operations: internal epoxy, external white primer, and 4 color offset printing. Then it arrives at press P2 with punch die D4L for the final bodyline operation, punching. Each strip is 1040 mm long and 220 mm wide. We punch rectangular body blanks from it. Each blank is 518 mm long. That's pi times 165 mm, the container circumference, and 210 mm wide, the body height. How many blanks from one strip? 1040 divided by 518 gives us exactly 2 blanks per strip. The gap between them is just 4 mm. 1040 minus 2 times 518 equals 4. That's 0.4% scrap, practically nothing. You can see the color coding in the diagram. Green is used material, red is scrap. Almost the entire strip becomes product. Below the diagram there's an important detail, how this flat blank becomes a container body. The 518 mm blank is rolled into a cylinder. The circumference matches because 518 equals pi times 165. The side edges overlap 2 mm and are resistance welded to form the side seam. Then a circular bottom blank is placed on one end and a double seaming machine crimps the bottom to the body, creating an airtight seal. The result is a sealed container body, open at the top, ready for paint filling. The yield from one sheet is 8 blanks, 4 strips times 2 blanks each. The bottom line uses a different sheet, item code TPO20900 extension 600. Thinner at 0.20 mm because the bottom doesn't need the structural strength of the body wall. It weighs 0.85 kilograms and costs 95 rupees per sheet. Two operations here, slitting and circular punching. First, slitting. The sheet is 900 mm wide. Each strip needs to be 170 mm. That's the 165 mm blank diameter plus 5 mm clearance. 900 divided by 170 gives us 5 strips, using 850 mm. That leaves 50 mm of edge waste, 5.5% scrap at slitting. You can see the red strip at the edge of the diagram. Slit scrap is 0.047 kilograms per sheet. Now the circular punching, and this is where the math gets interesting. Each strip is 600 mm long and 170 mm wide. We punch circles of 165 mm diameter. How many circles fit? 600 divided by 170 gives us 3 blanks per strip. But look at the scrap. Strip area is 102,000 square millimeters. 3 circles occupy just 64,147 square millimeters. The skeleton scrap, all the material between and around the circles, is 37,853 square millimeters. That's 37.1% waste. You can see the light blue skeleton waste surrounding the 3 green circles in the diagram. This is the inherent geometry of punching circles from rectangles. No matter how you optimize the nesting, you cannot significantly reduce this scrap with single row punching. It's physics, not a manufacturing deficiency. Punch scrap is 0.059 kilograms per strip. The yield is 15 blanks per sheet, 5 strips times 3 blanks each. Per shift of 7,500 bottoms, 500 sheets at 95 rupees each, 47,500 rupees. Slit scrap 23.5 kilograms, punch scrap 147.5 kilograms, total 171 kilograms. At 25 rupees per kilogram, that's 4,275 rupees in scrap recovery. The lid line follows the same pattern as the bottom, with 2 key differences. First, the lid is thicker, 0.28 mm instead of 0.20 mm. Same thickness as the body. Why? Because the customer opens and closes the lid repeatedly, with a screwdriver or a coin. So it needs the rigidity to survive repeated prying without deforming. This sheet is weighing 1.19 kilograms, costing 120 rupees. Second, the lid diameter is 170 mm, not 165 mm. The diagram explains why. The body outer diameter is 165 mm, but the lid needs 2 mm overhang on each side. That's 169 mm, plus 1 mm for the curl allowance where the lid edge curls inward to grip the body rim. Total, 170 mm. Slitting gives us 5 strips of 175 mm from the 900 mm width. Edge waste is just 25 mm to 2.8%, better than the bottom line's 50 mm because 5 times 175 equals 875, closer to 900. Slit scrap is 0.033 kilograms per sheet. Circular punching. 3 blanks of 170 mm from each 600 mm strip. Skeleton scrap is 35.1%, slightly better than the bottom line's 37.1% because the larger circle is more efficient relative to the strip width. Punch scrap is 0.081 kilograms per strip. Per shift, 500 sheets at 120 rupees equals 60,000 rupees. Slit scrap 16.5 kilograms, punch scrap 202.5 kilograms, and the total is 219 kilograms. Scrap recovery 5,475 rupees. This page shows all 5 bodyline operations in sequence, exactly as they appear in the ERP work order. Operation 1, slitting at shear M1, 938 sheets become 3,750 strips. Operation 2, internal epoxy coating at coating line CL1. The strip gets a gold epoxy lacquer on the inside face, oven cured at 200 degrees Celsius. This protects the tin from the paint chemicals inside. Operation 3, external white primer, same coating line CL1 second pass. White primer on the outside face creates the print surface. Operation 4, offset printing at printing press PP1. 4-color brand artwork, the Asian Paints Royale design, printed on the white prime surface. This is operation cost only, no material consumed. Operation 5, body blank punching at press P2 using punch die D4L. 2 rectangular blanks of 518 by 210 mm punched from each strip. 3,750 strips become 7,500 blanks plus 3.75 kilograms of scrap. After step 5, the body blank is rolled, welded, flanged, and seamed with the bottom blank. Steps 6 through 12 are not shown in this demo, but they follow the same ERP pattern, same screens, same job cards, same material tracking. Now the numbers that matter to the business. The complete material cost for one shift of 7,500 containers and 7,500 lids. Body line, 938 sheets at 235 rupees each. Rupees 2,20,430. Plus 3.75 kilograms of internal epoxy at 320 rupees per kilogram is 1,200 rupees. Plus 7.5 kilograms of white primer at 280 rupees per kilogram is 2,100 rupees. Bodyline subtotal, rupees 2,23,730. Scrap is just 4.65 kilograms with 116 rupees recovery, negligible on the bodyline. Bottom line, 500 sheets at 95 rupees each, 47,500 rupees. Scrap here is significant, 171 kilograms, with 4,275 rupees recovery. Lid line, 500 sheets at 120 rupees each, 60,000 rupees. Scrap is 219 kilograms with 5,475 rupees recovery. Shift grand total, 331,230 rupees in material cost. Total scrap generated, 394.65 kilograms. Scrap recovery at 25 rupees per kilogram, 9,866 rupees. Net material cost after scrap recovery, 321,364 rupees. And the number that drives pricing decisions, per unit material cost. Container body plus bottom, 35 rupees and 58 paise. Lid, 7 rupees and 27 paise. Complete set, 42 rupees and 85 paise. Daily production across 2 shifts, 15,000 sets. Daily material cost, 642,728 rupees. Daily scrap, 789 kilograms. Note that these are raw material costs only. Operation costs, labor, electricity, consumables, are tracked separately in the ERP system per workstation with hourly rates. The BOM rolls up both material and operation costs to give the full product cost.
Now that you understand the engineering and material economics behind the 4-liter container, let's see how the ERP system manages all of this, from daily transactions to shop floor operations. Let me log into the system. This is tinpack.bharatclouds.com, TinPack Industries ERP system, hosted on the cloud. Accessible from any browser, any device, the production manager can check work order status from his phone on the shop floor. The purchase head can approve POS from home, and the MD can review dashboards from anywhere. This is the home workspace, the first screen every user sees after login. On the left, you have the sidebar. This is your navigation panel with all the modules: home, accounting, buying, manufacturing, shop floor, stock, selling, quality, and more. Each of these is a workspace, a dedicated area for a specific business function. In the center, you see shortcuts and quick actions relevant to your role. At the top right, you have notifications. The bell icon shows pending approvals, workflow alerts, and system notifications. If a purchase receipt is waiting for quality inspection approval, the QC manager sees it here immediately. No emails to chase, no papers to sign, everything flows through the system. Now, this search bar at the top, in ERP Next, we call it the Awesome bar, and it truly is awesome. This is the fastest way to navigate the entire system. You don't need to remember menu paths or click through multiple screens. Let me show you what I mean. If you know a document number, just type it directly. The system opens it instantly. No need to go to selling, then sales order, then search. One step, or type a customer name, Asian Paints, and it shows you everything related to that customer. Sales orders, delivery notes, invoices, even the customer master record. It's a universal search across every document in the system. The Awesome bar searches across items, customers, suppliers, documents, reports, and even settings. It's like having Google for your entire business. Everything is one search away. Next to the search bar, you'll notice the Help section. This is built into every screen in the system. If a new user is creating a purchase order for the first time and isn't sure what a field means, they can click the Help icon right on that field and get a contextual explanation. No need to call IT or read a manual. ERP Next also has complete documentation accessible from here, setup guides, workflow explanations, and video tutorials. For TinPack, we've also configured custom tooltips on fields that are specific to tin manufacturing, like the sheet grade field on the item master, or the die stroke counter on the tool master. The goal is that after initial training, the system should be self-explanatory. The help is always right there where you need it. Role-based access control. Right now, I'm logged in as administrator, so I can see everything. All workspaces, all modules, all data. But in a real production environment, every user sees only what they need to see. This is controlled by roles and permissions. A sales manager at TinPack would log in and see the selling workspace, sales orders, quotations, customer records, and sales reports. They can create new quotations, check order status, and see delivery timelines. But they cannot see the manufacturing workspace, they cannot see purchase prices, and they cannot access accounting entries. Their view of the system is limited to exactly what their job requires. Same for the production supervisor, the purchase manager, the quality inspector, and the storekeeper. And the MD or director? They see the dashboards and reports across all modules, revenue, production output, quality metrics, stock levels, without needing to open individual transactions. A bird's eye view of the entire business. This role-based access does three things. First, it simplifies the interface. Every user sees a clean, uncluttered screen with only the options relevant to their job. No confusion, no overwhelm. Second, it enforces data security. Sensitive information like pricing, costs, and margins is visible only to authorized roles. And third, it creates accountability. Every action is logged against the user who performed it. You know exactly who approved that purchase order, who rejected that quality inspection, and who completed that job card. The system supports unlimited users. You can have 10 operators on the shop floor, each logging their own job cards on tablets, simultaneously with the purchase team processing receipts and the accounts team reconciling invoices. Everyone works in their own workspace, on their own data, without stepping on each other. Now that you've seen how the system is organized, let me walk you through the master data, the foundation on which all transactions run. We'll look at items, BOMs, warehouses, and workstations, the building blocks of TinPack's manufacturing process. Let's start with who we do business with. Customer master. Our customer list: Asian Paints Limited, Nerolac Paints Limited, Burger Paints, Kansai Nerolac. Each customer record holds their billing address, shipping address, GST details, payment terms, and credit limits, everything needed to generate an invoice without re-entering data. On the supply side, supplier master: Tata Tinplate Company for body and lid sheets, JSW Steel Tinplate Division as an alternate source, and Hind Prakash Industries for lacquers and coatings. Each supplier has a scorecard that tracks delivery performance and quality rejection rates. We'll see that in action when we look at the purchase receipt. The Item Master. The Item Master is the backbone of the system. We have 21 items organized by item group. Let me walk through the product structure. At the bottom, raw materials. Tinplate sheets in 3 grades. TPO28880 extension 1040 for body. TPO20900 extension 600 for bottom. TPO28900 extension 600 for lid. Then lacquers and coatings, Lac Gold SB epoxy and paint white base primer. In the middle, work in progress items. Body strips, coated strips, printed strips, body blanks, bottom blanks, lid blanks. Each one represents the output of a specific operation. The system tracks stock at every stage. You know exactly how many coated strips are waiting for printing, how many blanks are ready for assembly. At the top, finished goods. FG container 4 LAP and FG lid 4 LAP. The items that appear on the sales order and delivery note. And scrap tinplate, because even scrap is an item with a value that gets tracked. Let me open a raw material item. This is our body sheet, 0.28 mm thickness, 880 by 1040 mm. Notice the key fields. Item group is tinplate sheets, UOM is nose for individual sheets, and it's marked as a stock item with maintain stock enabled. The default warehouse is tinplate store. When a purchase receipt is created, material lands here automatically. Warehouse is master. Every item has a home. Our warehouse structure mirrors the physical factory layout. Raw materials start in tinplate store and lacquer store. When production begins, material moves to punching WIP, the work in progress warehouse for the press line. Finished components go to body blank store. Final assembled containers go to finished goods. That's where the delivery note picks from. 2 special warehouses. Scrap warehouse collects skeleton waste from circular punching, tracked by weight and sold to scrap dealers monthly. And rejected store. Material that fails quality inspection is segregated here. Physically separate, digitally separate. Nobody accidentally uses rejected sheets in production. BOM, bill of materials. This is the most important master in the system, the bill of materials. Let me show the tree view for our finished container. BOM tree shows the complete product structure, every material, every operation, every cost, all in one view. At the top, FG container 4 LAP, the finished container. It's made from container 4L body, which is made from blank 4L plus bottom 4L. The body blank comes from a printed strip, which comes from a primed strip, which comes from a coated strip, which comes from a plain strip, which comes from the raw tinplate sheet. 7 levels deep. Each level has its own BOM with the exact material quantities and operations. The body sheet BOM says one sheet produces 4 strips. The strip BOM says one strip produces 2 blanks. The system multiplies through all levels to calculate that one finished container needs 0.125 sheets, 1/8 of a sheet, because 8 blanks per sheet. When we create a work order for 15,000 containers, the system calculates backwards through this tree. 15,000 containers need 1,875 sheets, 7.5 kilograms of epoxy, 15 kilograms of primer. Automatic, accurate, no spreadsheets. Workstations and operations master. Every machine on the shop floor is a workstation with an hourly operating cost. Shear M1 for slitting, coating line CL1 for lacquering and priming, printing press PP1 for offset printing, and press P2 for punching. The hourly rates drive the operation cost in the BOM, so product costing includes both material and machine time. 9 operations defined: slitting, internal epoxy coating, external white primer, offset printing, punching, end blank punching, bottom seaming, and assembly operations. Each operation links to a workstation and has a standard time. When job cards are created, operators log actual time against this standard, giving you variance analysis.
Now let's see how a real business cycle flows through these masters, starting with a sales order from Asian Paints. Sales order. Asian Paints has placed an order for 15,000 containers and 15,000 lids. 2 line items. Finished good container at 65 rupees each, total rupees 9,75,000, and finished good lid at 15 rupees each, total rupees 2,25,000. Grand total, rupees 12 lakhs. Why 2 separate line items? Because containers and lids are delivered separately. Asian Paints fills the container with paint at their factory, then press fits the lid. The ERP tracks each independently through production, inspection, and delivery. Notice the status: to deliver and bill. This tells the sales team and the production team that this order is confirmed, material needs to be manufactured and shipped, and an invoice needs to be raised. One glance, complete clarity. The delivery warehouse is set to finished goods. When we create a delivery note later, the system will pull stock from this warehouse. If stock isn't available, it won't let you deliver. No overselling, no phantom shipments. After manufacturing is complete, we create a delivery note. This was created directly from the sales order. 14,100 containers and 14,100 lids dispatched, a partial delivery against 15,000. Why not the full order? Two reasons, and both are tracked by the system. First, the quality gate at receiving. During the purchase receipt, 200 lid sheets were rejected for edge waviness. That's 200 sheets that never entered production. Less raw material, it means less finished goods out. The system didn't allow those rejected sheets to be used. They sat in a rejected store, physically and digitally blocked from the production line. Second, manufacturing scrap at every operation produced slightly fewer good pieces than it received. Across 5 operations on the body line, the cumulative yield was about 94%. Both of these, incoming quality rejections and in-process scrap, are tracked automatically. The system doesn't hide the shortfall or let anyone fudge the numbers. 15,000 was ordered, 14,100 was produced, 14,100 was delivered. The gap is explained, documented, and traceable. That's the difference between running a factory on spreadsheets and running it on an ERP. We produced what the factory yielded, and the system handles the partial delivery naturally. The remaining 900 units stay as a backlog, and next production batch picks it up. Delivery value: 14,100 times 65 rupees plus 14,100 times 15 rupees is rupees 11 lakhs 28,000 out of the rupees 12 lakh order. From the sales order, we can create delivery note, work order, sales invoice, payment request, and material request, and everything auto-populates. No reentry, no mismatch.
Purchase cycle. On the supply side, we raised a purchase order to Tata Tinplate Company for the raw material needed for this production run. 2 items, 2,000 body sheets, TP028 880 by 1040 at 235 rupees each, total rupees 4 lakh and 70,000. And 1,500 lid sheets, TP028 900 by 600 at 120 rupees each, total rupees 1 lakh 80,000 PO total, rupees 6 lakhs and 50,000. The quantities come directly from the BOM calculations. 15,000 containers need 1,875 body sheets. We ordered 2,000 to have a small buffer. Bottom sheets were already in stock from a previous purchase, so no order needed there. The system helps you order only what's missing. Status shows completed, 100% received. Let's see what happened at receiving. When Tata Tinplate's truck arrived, the store's team created this purchase receipt. And this is where the story gets interesting. Row 1, body sheets. 2,000 received, 2,000 accepted, 0 rejected. The quality inspection linked here, which shows status accepted. All 2,000 sheets went to Tinplate store. Clean receipt. Row 2, lid sheets. 1,500 received, but look, accepted quantity is only 1,300. Rejected quantity, 200. And the rejected warehouse is set to rejected store. What happened? The QC team sampled 30 sheets from this lot and found edge waviness exceeding the maximum specification. Surface scratches were also detected. 200 sheets failed incoming inspection. The system did 3 things automatically. It split the stock, 1,300 good sheets to Tinplate store, 200 rejected sheets to rejected store. It linked the quality inspection record as proof, and it updated the supplier's performance data. No manual stock adjustment needed. No separate rejection entry. The quality gate is built into the receiving process. The purchase invoice is created from the purchase receipt. The system posts to accounts payable and tracks payment due dates. For the rejected 200 sheets, TinPack can raise a debit note or negotiate a replacement with the supplier. The rejection is documented and linked.
Manufacturing cycle, work orders, job cards, material transfer, manufacture, assembly. Work orders. Manufacturing runs on 3 parallel production lines. 3 work orders, 1 per production line, body, bottom, and lid, each for 15,000 pieces, all running in parallel, all now completed. The body line, work order for blank 4L, quantity 15,000. This is the longest chain with 5 operations. 5 operations in exact factory sequence: slitting at shear M1, internal epoxy coating at coating line CL1, external white primer on the same coating line, offset printing at printing press PP1, and punching at press P2. Each operation shows completed status with the actual completed quantity. Notice, use multi-level BOM is checked. This is the key design decision. Instead of creating 7 separate work orders for 7 BOM levels, 1 work order with multi-level BOM flattens everything into a single production run. Raw materials go in at the start: sheets, epoxy, primer. Finished blanks come out at the end. Each operation in between is tracked through its own job card, but without unnecessary intermediate warehousing. Required items, calculated from the multi-level BOM. 1,875 sheets, 7.5 kilograms epoxy, 15 kilograms primer. All showing transferred material has moved from stores to the WIP warehouse. Bottom line, 2 operations, slit and circular punch. Lid line, same pattern. All 3 ran in parallel on the shop floor, tracked independently in the system. Job cards. Each operation creates a job card. This is what the shop floor operator sees. 9 job cards across 3 lines, all completed. The slitting job card, operated by Ravi Jadhav. This is the operator's workspace. Time log. Started at 6 a.m., finished at 7:15 a.m. 75 minutes for 14,850 strips. The system calculates actual time per piece from this. Compare it against the standard time in the BOM and you get efficiency metrics. Completed quantity, 14,850 out of 15,000 target. 150 strips lost. That's 1% scrap from edge trimming. The remarks capture the details. Body strips cut from 880 by 1040 sheets. 1% edge trim scrap. Operator, Ravi Jadhav. Printing, operated by Manoj Pawar. 14,700 produced, 90 rejected for print registration errors, 0.6% scrap. Different operator, different operation, same structured tracking. Punching, Amit Shind. 14,400 produced, 300 rejected for edge burr. 2% scrap, the highest rejection rate on the body line. Over time, this data tells the production manager, is it the die wearing out? Is it the material grade? Is it the operator technique? The system gives you the data to answer these questions. Bottom line punching, Praveen Kale. 14,650 produced, 250 rejected for flange irregularity. Same operator runs the lid line punching too. Phosphorus monoxide job 0009, with 14,600 produced. You can compare his performance across different materials and shifts. Assembly and finished goods. Once all 3 lines complete, the components come together. Assembly happens in 2 stages. First, body blanks and bottom blanks are seamed together into container bodies. The repack entry shows, blank 4L in, bottom 4L in, container 4L body out. 14,100 units, limited by the body blank yield. Second, container bodies are labeled as finished goods. Container 4L body becomes finished good FG container 4L AP. Similarly, lid blanks become finished good FGID 4L AP. Both move to the finished goods warehouse, ready for dispatch. Why 14,100 and not 15,000? Because scrap accumulated at every step, 150 at slitting, 30 at coating, 30 at primer, 90 at printing, 300 at punching. The system tracked every piece lost. 94% yield across 5 operations, exactly what you'd expect in a real factory. Stock balance and stock ledger. The stock ledger is the detailed audit trail. Let me filter by our body sheet, TPO 28880 by 1040, and trace its journey through the system. First entry, 2,000 sheets received into tinplate store via the opening stock receipt. Then the purchase receipt brings in another 2,000 from Tata Tinplate. Next, 1,875 sheets transferred from tinplate store to punching WIP for production. And finally, 1,800 sheets consumed from WIP in the manufacturing entry, producing finished body blanks. Every movement has a timestamp, a voucher type, a voucher number, and a running balance. For any stock discrepancy, this is where you investigate. The data is immutable. Once posted, it cannot be edited, only reversed with a new entry. Complete audit compliance. And if I switch to the lid sheet, you can see the purchase receipt split clearly. 1,300 sheets into tinplate store, 200 sheets into rejected store, both from the same receipt, same transaction, automatically separated by the quality inspection result. This is the traceability that audit teams look for. Tool management. Beyond standard ERP transactions, the system includes shop floor management tools specific to manufacturing. The tool master tracks every die and punch on the factory floor. We have 5 punch dies registered, D4L body for the rectangular body blank, D4L BTM for the 165mm bottom circular blank, and D4L lid for the 170mm lid blank. Plus 2 1-liter dies for a different container size. Each die record captures the tool number, description, cavity count. This body die has 2 cavities, meaning it punches 2 blanks per stroke, and the current status. The 1-liter bottom die is marked, under maintenance, so the system won't allow it to be assigned to a production job card until it's restored to active. Tool tracking is critical in tin manufacturing. A worn punch die produces blanks with edge burr, which we saw in the job card rejections. When rejection rates spike on a specific die, this master gives the maintenance team the history they need. The system also includes machine breakdown logging and knock rejection tracking. These capture downtime events with reason codes and shift-wise rejection data by operator and machine. Over months, this data reveals patterns: which machines break down most, which shifts have higher rejections, which operators need retraining. It turns shop floor chaos into actionable data. Quality cycle. Incoming quality inspection. Quality is not a department, it's built into every transaction. Let me show the 3 quality gates. First, incoming inspection. This is the body sheet inspection we just discussed. Template. Incoming tinplate sheet. The system loaded the inspection parameters automatically. Look at the readings: thickness, coating weight, surface roughness, edge waviness. Each has a minimum and maximum specification. The inspector entered the measured values. The system compared against the spec and determined. Accepted. Sample size: 20 sheets from a lot of 2,000. The inspection is linked to the purchase receipt. Complete traceability from supplier to shop floor. Now the lid sheet inspection, same template, but different result. Edge waviness measured 0.45 mm against a maximum of 0.3 mm. Status: rejected. This rejection triggered the automatic stock segregation we saw on the purchase receipt. 200 sheets moved to rejected store, digitally and physically separated from production material. An operator on the shop floor cannot accidentally pick rejected sheets because the system won't allow a material transfer from the rejected store to WIP. In-process quality templates. Have 4 in-process inspection templates ready to use. Body strip after slitting, checks strip width and edge quality right after the shear. Epoxy-coated strip, verifies coating adhesion and thickness after the oven cure. Body blank after punching, dimensional check on the rectangular blank. And circular blank for bottom and lid, diameter and surface finish verification. These can be triggered at any production stage. When a foreman suspects a problem, say the coating looks uneven, he creates an inspection right from the job card. The template loads, he enters readings, and the system decides, pass or fail. Documented, time-stamped, traceable. Outgoing quality inspection. Final gate, outgoing inspection before dispatch. This is linked to the delivery note. Template. Sealed container, final. 50 containers sampled from the lot of 14,100. The inspection covers everything the customer cares about: leak test, seam tightness, print quality, dimensional accuracy. All parameters passed. Status: accepted. Only after this CHI was approved could the delivery note be submitted. The system enforces this. You literally cannot dispatch goods without quality clearance. This is the audit trail Asian Paints expects from their suppliers. For any container that reaches their factory, TinPack can trace back which batch of tinplate it came from, which operator processed it at which workstation, which QC inspector cleared it, and when it was shipped. End-to-end traceability. Accounting. The accounting module ties everything together. Every transaction we've seen, purchases, manufacturing, deliveries, automatically posts to the books. No separate data entry, no month-end reconciliation. Payables tracks what you owe suppliers, purchase invoices, payment entries, and supplier ledger summaries. The purchase receipt we saw from Tata Tinplate flows directly here. Receivables tracks what customers owe you, sales invoices, payment collection, and aging analysis. The delivery note to Asian Paints generates the invoice that appears here. And financial reports gives the management view, general ledger, trial balance, profit and loss, balance sheet, cash flow. All generated in real time from the same transactions the shop floor and stores teams created. One system, one source of truth, from the factory floor to the boardroom. What you've seen today covers the complete business cycle, from a sales order to purchase, through quality gates at every stage, manufacturing with operator-level tracking, assembly, and delivery with full traceability. The 4-liter container we demonstrated has about 40 operations in reality. We showed 9 of them. The remaining 31 follow exactly the same pattern, same screens, same quality checks, same material tracking. The system scales with your process complexity. Thank you for watching.